this was that list. Gauss, Galois, Euler, Leibniz, Newton, Lagrange, Hamilton, Riemann. Gauss was a funny one in there, but I guess so is Euler. Well, but yeah, more Gauss. Although quintics, viscosity, bruh. What about bro? Okay, yeah. Well, of course. Let's just do this. Easy, easy. Wow, wow, wow. Well, but okay, that is kind of a lot to chew on at once. But how about like I guess I could just do marker on paper. Totally doing number file right now. That is a main choice. Not number file. Okay. That is hilarious. Anyway, I don't know what I'm looking for in particular. I just kind of like get my mouth around some math. I really want to hit like, I don't know, bro, also this feels like it's dying. Optics, but then that goes to like, I don't think any of these people are optics except for Newton. I mean, I'm particularly interested in, as far as curvature goes, I guess Gauss seems like the right one. But then yeah, so this, I really don't have a basis in this. I feel like somehow I missed Gauss. That seems impossible, but maybe I just like was not on that wavelength at the time. Seems like it. The Gaussian curvature or Gauss curve K of a smooth surface in three-dimensional space at a point is the product of the principal curvatures K1 and K2 given at that point. Written as K is the product of the curvatures K1 and K2. Okay. Well said the first time. For example, a sphere of radius r has Gaussian curvature 1 over r squared everywhere. What means this to me? How do I locate? I'm confused about how it, like, the Gaussian curvature changes across the sphere by height. So r squared is a vector differential geometry, maybe. Or I guess they just have a coordinate system and a... What is... Whoa. What is this? Theorema egregium. Okay, so Gauss... Okay, when was Gauss? 1827. Bro, I think I just need a pen again. Or just to go harder with this thing. So, 777 in 1855. But 1827, he was talking about, and he lived in the Holy Roman Empire in Brunswick. Wow. Sounds like a very impressive place to live when you put it that way. Probably just a house. Probably not even that. Probably just a hole in the wall. Yeah, okay, so I know him in relation to geodesy, but I've really never studied his math, it seems like. Seems so crazy. A heliotrope. This looks like it could be a helicopter or a telescope. An arc measurement needs a precise astronomical determination of at least 2 points in the network. Bro, Gauss was so network focused. I find that so interesting. Yes, bro. Oh my goodness, I just want to study this world until I can't anymore somehow. Okay, I gotta keep my stuff grounded here. But okay, his math. I don't know what to do here. I really want to focus. Kind of funny, I feel like I'm learning to pass the marshmallow test right now. Better late than never, suppose. Probably just keep learning this forever. Gauss-Legendre quadrature. Bro, what are you trying to tell me? I'm sure I would know if we were in some kind of context. Blah blah blah. All this Gauss stuff is so like oddly put. What is this article? Oh, it's specifically about whatever a Gaussian quadrature is. It's like a integral estimate of something. Let me out. Okay. This finding in differential geometry of Gauss's in 1827 concerns the curvature of surfaces. The theorem says that Gaussian curvature can be determined entirely by measuring angles. Bro. Dot dot dot. I cannot get through this result. The point is, the theorem says that Gaussian curvature can be determined entirely by measuring angles, distances, and their rates of change on a surface without reference to the particular manner in which the surface is embedded in the ambient 3 Euclidean space. Huh, okay. Yeah, but you would need like a differential geometric distance map that flattens the 3 Euclidean map, right? So then you're just doing the same thing. And yeah, we're using a Mercator projection to get to 2 space. So how is this a finding? I feel like I must be missing what the point was. I mean, you're just proving that if you map to a 2 space, we can still measure curvature. It just will be odd. It'll just be like a contrived function which maps from 3 to 2. Or 2 back to a 3 curve on 2. That is pretty interesting though. And then you would get like cyclic and symmetric structures on a smooth projection That's pretty cool. Do you get a cyclic wave on a Mercator projection? Or no? Is that what it means to be conformal? That it doesn't introduce weird waviness? What is a non-conformal map? I mean, I guess I know the point. Yes. Okay, back to whatever the heck the finding is. Wait, that's that. In other words, the Gaussian curvature of a space does not change if one bends the space without stretching it. Huh. Yeah, I guess so. And the point of the Mercator projection is that I feel like it's weird to say that you're not stretching it. In this projection, you're not stretching it at all? What's happening at this pole? You're bending it out? That's why it's so hideous at the poles? Huh. Okay. That's so great. I mean, it's a good map. But like, yeah, when you... The Gaussian curvature is intrinsic invariant. Wait, is an intrinsic invariant of a surface. What a beautiful image to select. Gaussian curvature is an intrinsic invariant. Yeah. So like I was saying, it's like you get emergent, well, symmetries. I guess it's not emergent, but it kind of feels emergent in that context. Isometries of the Euclidean plane. Bro, that stuff is so pretty. Get it all out of here. I don't want to see it. And then conformal maps. Why are you showing me a Laplace transform? Jabroni. What is this? That's not Laplace. It's not Laplace. Everything is just showing me the same. Where is this transform coming from? They're all the same. Okay, gosh, this world is such a soup of stuff. Let me out. Gauss. JK, don't let me out. Gauss. Bending. Presented the theorem in this manner. If the curved surface is developed upon any other surface, whatever, the measure of curvature at each point remains unchanged. I'm gonna go wash my eye. What's going on here? So, okay, what does geodesy give us? And, well, okay, what is all of this? I hate this. There's so much stuff to look at. Have a little bit of but let's just